Hi, I'm back with you again, reading Python Programming by John Zelle. This is the third edition, and we're learning about computer science. Starting today, I'll be reading Chapter 1. I've already been through the introduction and the preface. So, Chapter 1, we have some objectives. Number 1, to understand the respective roles of hardware and software in computing systems, to learn what computer scientists say and the techniques that they use, and third, to understand the basic design of a modern computer, then to understand the form and function of computer programming languages, next, to begin using the Python programming language, and finally, to learn about chaotic models and their implications for computing. Section 1.1, the universal machine. Almost everyone has used a computer at one time or another. Perhaps you've played computer games or used a computer to write a paper or shop online, listen to music, or connect with friends via social media. Computers are used to predict the weather, design airplanes, make movies, run businesses, perform financial transactions, and control factories. Probably even more. Have you ever stopped to wonder what exactly a computer is? How can one device perform so many different tasks? These basic questions are a starting point for learning about computers and computer programming. Just seeing a notification on there. A modern computer can be defined as a machine that stores and manipulates information under the control of a changeable program. There are two key elements to this definition. The first is that computers are devices for manipulating information. This means we can put information into a computer and it can transform the information into new useful forms and then output or display the information for our interpretation. Computers are not only machines that manipulate information. When you use a simple calculator to add up a column of numbers, you are entering information, the numbers, and the calculator is processing the information to compute a running sum, which is then displayed. Another simple example is a gas pump. As you fill your tank, the pump uses certain inputs: the current price of gas per gallon, the signals from a sensor that reads the rate of gas flowing into your car. The pump transforms this input into information about how much gas you took and how much money you owe. I did not check. Okay, that's fine. Sorry for the interruptions. We would not consider either the calculator or the gas pump as full-fledged computers, although modern versions of these devices may actually contain embedded computers. They are different from computers in that they are built to perform a single and specific task. This is where the second part of our definition comes into the picture. Computers operate under the control of a changeable program. What exactly does this mean? A computer program is a detailed step-by-step set of instructions telling a computer exactly what to do. If we change the program, then the computer performs a different sequence of actions and hence performs a different task. It is this flexibility that allows your PC to be at one moment a word processor, at the next moment a financial planner, and then later on an arcade game. The machine stays the same, but the program controlling the machine changes. Every computer is just a machine for executing or carrying out programs. There are many different kinds of computers. You might be familiar with Macintoshes, PCs, laptops, tablets, and smartphones, but there are literally thousands of other kinds of computers, both real and theoretical. One of the remarkable discoveries of computer science is the realization that all these different computers have the same power. With suitable programming, each computer can basically do all the things that any other computer can do. In this sense, the PC that you might have sitting on your desk is really a universal machine. It can do anything you want it to do, provided you can describe the task to be accomplished in sufficient detail. Now that's a powerful machine. But sorry, I'm going to throw commentary in here. No matter what you do, the computer does not have legs and arms. So you'd have to make some modifications to the machine before it can do anything requiring that type of mobility. All right, but as far as calculating goes, that's fine. So 1.2, we're on to section 1.2, program power. You have already learned an important lesson of computing: software, programs, rules, the hardware, the physical machine. So the software rules the hardware. Got it. It is the software that determines what any computer can do. Without software, computers would just be expensive paperweights. The process of creating software is called programming, and that is the main focus of this book. Computer programming is a challenging activity. Good programming requires an ability to see the big picture while paying attention to the minute detail. Not everyone has the talent to become a first-class programmer, just as not everyone has the skills to be a professional athlete. However, virtually anyone can learn how to program computers. Good, there's hope for me. With some patience and effort on your part, this book will help you to become a programmer. There are lots of good reasons to learn programming. Programming is a fundamental part of computer science and is therefore important to anyone interested in becoming a computer professional. But others can also benefit from the experience. Computers have become a commonplace tool in our society. Understanding the strengths and limitations of the tool requires an understanding of programming. Non-programmers often feel they are slaves of their computers. Programmers, however, are truly in control. If you want to become a more intelligent user of a computer, then this book is for you. Programming can also be loads of fun. It is an intellectually engaging activity that allows people to express themselves through useful and sometimes remarkably beautiful creations. Believe it or not, many people actually write computer programs as a hobby. Programming also develops valuable problem-solving skills, especially the ability to analyze complex systems by reducing them to interactions of understandable subsystems. As you probably know, programmers are in great demand. More than a few liberal arts majors have turned a couple of computer programming classes into a lucrative career option. Computers are so commonplace in the business world today that the ability to understand and program computers might just give you the edge over your competition, regardless of your occupation. When inspiration strikes, you could be poised to write the next killer app. Section 1.3. What is computer science? You might be surprised to learn that computer science is not the study of computers. A famous computer scientist named Edgar Dijkstra, I am guessing, I do not know that name, once quipped that computers are to computer science what telescopes are to astronomy. The computer is an important tool in computer science, but it is not itself the object of study. Since a computer can carry out any process that we can describe, the real question is, what processes can we describe? To put it another way, the fundamental question of computer science is simply what can be computed. Computer scientists use numerous techniques of investigation to answer this question. The three main ones are design, analysis, and experimentation. One way to demonstrate that a particular problem can be solved is to actually design a solution. That is, we develop a step-by-step process for achieving the desired result. Computer scientists call this an algorithm. That's a fancy word that basically means a recipe. The design of algorithms is one of the most important facets of computer science. In this book, you will find techniques for designing and implementing algorithms. One weakness of design is that it can only answer the question, what is computable? In the positive. If I can devise an algorithm then the problem is solvable. However, failing to find an algorithm does not mean that a problem is unsolvable. It may mean that I'm just not smart enough, or I haven't hit upon the right idea yet. This is where analysis comes in. That word yet is important. I'm just not there yet. Analysis is the process of examining algorithms and problems mathematically. Computer scientists have shown that some seemingly simple problems are not solvable by any algorithm. Other problems are intractable. The algorithms that solve these problems take too long or require too much memory to be of practical value. Analysis of algorithms is an important part of computer science. Throughout this book, we will touch on some of the fundamental principles. Chapter 13 has examples of unsolvable and intractable problems. They should have used the word yet. They're just unsolvable yet. Some problems are too complex or ill-defined to lend themselves to an analysis. In such cases, computer scientists rely on experimentation. They actually implement systems and then study the resulting behavior. Even when theoretical analysis is done, experimentation is often needed in order to verify and refine the analysis. For most problems, the bottom line is whether a working, reliable system can be built. Often we require empirical testing of the system to determine that this bottom line has been met. As you begin writing your own programs, you will get plenty of opportunities to observe your solutions in action. I have defined computer science in terms of designing, analyzing, and evaluating algorithms, and this is certainly the core of the academic discipline. These days, however, computer scientists are involved in far-flung activities, all of which fall under the general umbrella of computing. Some examples include mobile computing, networking, human-computer interaction, artificial intelligence, computational science, using powerful computers to model scientific processes, databases and data mining, software engineering, web and multimedia design, music production, management information systems, and computer security. Wherever computing is done, the skills and knowledge of computer science are being applied. So above that paragraph, I see figure 1.1, a functional view of a computer, and that's going to come in section 1.4. So I'm going to show an image. You guys can see the picture. Image 1.1. And I'm going to read about figure 1.1 and see input devices there, CPU and main memory there, then output devices, and then secondary memory. Let's learn about those things and the functional view of a computer. Section 1.4, Hardware Basics. You don't have to know all the details of how a computer works to be a successful programmer, but understanding the underlying principles will help you master the steps we can go through to put our programs into action. It's a bit like driving a car. Knowing a little about the internal combustion engines helps to explain why you have to do things like fill the gas tank, start the engine, step on the accelerator, and so on. You could learn to drive by just memorizing what to do, but a little more knowledge makes the whole process much more understandable. Let's take a moment to look under the hood of your computer. Although different computers can vary significantly in specific details, at a higher level, all modern digital computers are remarkably similar. Figure 1.1 above shows a functional view of a computer. The central processing unit, the CPU, is the brain of the machine. This is where all the basic operations of the computer are carried out. The CPU can perform simple arithmetic operations like adding two numbers, and can also do logical operations like testing to see if two numbers are equal. The memory stores programs and data. The CPU can directly access only information that is stored in main memory, called RAM, or random access memory. Main memory is fast, but it is also volatile. That is, when the power is turned off, the information in the memory is lost. Thus, there must also be some secondary memory that provides more permanent storage. In a modern personal computer, the principal secondary memory is typically an internal hard disk drive or a solid state drive. An HDD stores information as magnetic patterns on a spinning disk, while an SSD employs electronic circuits known as flash memory. Most computers also support removable media for secondary memory, such as USB memory sticks, also a form of flash memory, and DVDs, digital versatile discs. That's the first time I'm learning that, which store information as optical patterns that are read and written by laser. Humans interact with the computer through input and output devices. You are probably familiar with common devices such as a keyboard, mouse, and monitor, the video screen. Information from input devices is processed by the CPU and may be shuffled off to the main or secondary memory. Similarly, when information needs to be displayed, the CPU sends it to one or more output devices. So what happens when you fire up your favorite game or word processing program? First, the instructions that compromise the program are copied from the more permanent secondary memory into the main memory of the computer. Once the instructions are loaded, the CPU starts executing the program. Technically, the CPU follows a process called the fetch executive cycle. The first instruction is received from the memory, decoded to figure out what it represents and the appropriate action carried out. Then the next instruction is fetched, decoded, and executed. The cycle continues, instruction after instruction. This is really all the computer does from the time that you turn it on until you turn it off again. Fetch, decode, and execute. It doesn't seem very exciting, does it? But the computer can execute this stream of simple instructions with blazing speed, zipping through billions of instructions each second. Put enough put enough simple instructions together in just the right way, and the computer does amazing things. Section 1.5, Programming Languages. Remember that a program is just a sequence of instructions telling a computer what to do. Obviously, we need to provide those instructions in a language that a computer can understand. It would be nice if we could just tell a computer what to do using our native language, like they do in science fiction movies. Computer, how long will it take to reach the planet Alfalfa at maximum warp? Computer scientists have made great strides in this direction. You may be familiar with technologies such as Siri from Apple, Google Now, Android, and Cortana, Microsoft. But as anyone who has seriously used such systems can attest, designing a computer program to fully understand human language is still an unsolved problem. Even if computers could understand us, human languages are not very well suited for describing complex algorithms. Natural language is fraught with ambiguity and imprecision. For example, if I say, I saw the man in the park with the telescope, did I have the telescope or did the man? And who was in the park? We understand each other most of the time only because all humans share a vast store of common knowledge and experience. Even then, miscommunication is commonplace. Computer scientists have gotten around this problem by designing notations for expressing computations in an exact and unambiguous way. These special notations are called programming languages. Every structure in a programming language has a precise form, or its syntax, and a precise meaning, that's its semantics. A programming language is something like a code for writing down the instructions that a computer will follow. In fact, programmers often refer to their programs as computer code, and the process of writing an algorithm in a programming language is called coding. Python is one example of a programming language and is the language that we will use throughout this book. Footnote: this edition of the text was developed and tested using Python version 3.4. Python 3.5 is now available. If you have an earlier version of Python installed on your computer, you should upgrade to the latest stable 3. Whatever version to try out these examples. Okay. Where's my little footnote? There. You may have heard of some other commonly used languages such as C++, Java, JavaScript, Ruby, Perl, scheme, or basic. Computer scientists have developed literally thousands of programming languages, and the languages themselves evolve over time, yielding multiple, sometimes very different versions. Although these languages differ in many details, they all share the property of having well-defined, unambiguous syntax and semantics. All of the languages mentioned above are examples of high-level computer languages. Although they are precise, they are designed to be used and understood by humans. Strictly speaking, computer hardware can understand only a very low-level language known as machine language. Daniel, please close my door. Suppose we want the computer to add two numbers. The instructions the CPU actually carries out might be something like this. Load the number from memory location 2001 into the CPU. Load the number from memory location 2002 into the CPU. Add the two numbers in the CPU. Store the results into location 2003. This seems like a lot of work to add up two numbers, doesn't it? Actually, it's even more complicated than that, because the instructions and the numbers are represented in binary notation as a sequence of zeros and ones. In a high-level language like Python, the addition of two numbers can be expressed more naturally. C equals A plus B. That's a lot easier for us to understand, but we need some way to translate the high-level language into the machine language that the computer can execute. There are two ways to do this. A high-level language can either be compiled or interpreted. A compiler is a complex computer program that takes another program written in a high-level language and translates it into an equivalent program in the machine language of some computer. Figure 1.2 shows a block diagram of the compiling process. The high-level program is called source code, and the resulting machine code is a program that the computer can directly execute. The dashed line in the diagram represents the execution of the machine code, also known as the running program. I'll show you figure 1.2, compiling a high-level language, and please disregard the highlighting I am using. I am reading from a used textbook. So this diagram here is what I am talking about next. So figure 1.2. An interpreter is a program that simulates a computer that understands a high-level language. Rather than translating the source program into a machine language equivalent, the interpreter analyzes and executes the source code in instruction by instruction. Rather than translating the source program into machine language equivalent, the interpreter analyzes and executes the source code instruction by instruction as necessary. What an awkward sentence. And please excuse the interruptions. I do have 4 children. They interrupt from time to time. Figure 1.3 illustrates this process. So figure 1.3, interpreting a high-level language. Again, disregard the highlighter there. It's source code program and inputs, computer running an interpreter, and outputs. The difference between interpreting and compiling is that compiling is a one-shot translation. Once a program is compiled, it may be run over and over again without further need for the compiler or the source code. In the interpreted case, the interpreter and the source are needed every time the program runs. Compiled programs tend to be faster since the translation is done once and for all. But interpreted languages lend themselves to a more flexible programming environment, as programs can be developed and run interactively. The translation process highlights another advantage that high-level languages have over machine language. That's portability. The machine language of a computer is created by the designers of a particular CPU. Each kind of computer has its own machine language. A program for an Intel i7 processor in your laptop won't run directly on an ARM v8 CPU in your smartphone. On the other hand, a program written in a high-level language can be run on many different kinds of computers as long as there is a suitable compiler or interpreter, which is just another program. As a result, I can run the exact same Python program on my laptop and on my tablet, even though they have different CPUs. They both sport a Python interpreter. Section 1.6, the magic of Python. This better be magical. Now that you have all the technical details, it's time to start having fun with Python. The ultimate goal is to make the computer do our bidding. To this end, we will write programs that control the computational processes inside the machine. You've already seen that there is no magic in this process, but in some ways, programming feels like magic. The computational processes inside the computer are like magical spirits that we can harness for our work. Unfortunately, those spirits only understand a very arcane language that we do not know. What we need is a friendly genie that can direct the spirits to fulfill all our wishes. Our genie is a Python interpreter. We can give instructions to the Python interpreter, and it directs the underlying spirits to carry out our demands. We communicate with the genie through a special language of spells and incantations. For example, Python. The best way to start learning about Python is to let our genie out of the bottle and try some spells. With most Python installations, you can start a Python interpreter in an interactive mode called a shell. A shell allows you to type Python commands and then displays the results of executing them. The specifics for starting a shell differ for various installations. If you are using the standard Python distribution for PC or Mac from www.python.org, you should have an application called Idle that provides a Python shell and, as we'll see later on, also helps you create and edit your own Python programs. The supporting website for this book has information on installing and using Python on a variety of platforms. When you first launch Idle or another Python shell, you should see something like this. Python 3.4.3, v3.43.3, colon 9b, 73, F1C3E 601, February 24, 2015, 224306. Oh my goodness, top copyright, credits, license for more information. The exact opening message depends on the version of Python that you are running and the system that you are working on. The important part is the last line, the arrow, arrow, arrow. It's a Python prompt indicating that our genie, the Python interpreter, is waiting for us to give it a command. In programming languages, a complete command is called a statement. Here is a sample interaction with a Python shell. Arrow, 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 print. Hello, world. Hello, world. Arrow, 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 print. 2 plus 3, inside parentheses. Next line 5, arrow, 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 print, in parentheses, in quotes. 2 plus 3 equals end quote, comma, 2 plus 3, end parentheses. 2 plus 3 equals 5. Here I have tried out 3 examples using the Python print statement. The first statement asks Python to display the literal phrase, hello world, exclamation point. Python responds in the next line by printing the phrase. The second print statement asks Python to print the sum of 2 and 3. The third print combines these 2 ideas. Python prints the part in quotes, 2 plus 3 equals, followed by the result of adding 2 plus 3, which is 5. This kind of shell interaction is a great way to try out new things in Python. Snippets of interactive sessions are sprinkled throughout this book. When you see the Python prompt arrow, arrow, arrow in an example, that should tip you off that an interactive session is being illustrated. It's a good idea to fire up your own Python shell and try the examples. Usually we want to move beyond one-line snippets and execute an entire sequence of statements. Python lets us put a sequence of statements together to create a brand new command or a function. It is an example of creating a new function called hello, arrow, 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 def. Hello, open parentheses, close parentheses, colon, next line, print, open parentheses, open quote, hello, end quote, end parentheses, next line, print, open parentheses, open quote, computers are fun, exclamation point, end quote, end parentheses, arrow, arrow, arrow. The first line tells Python that we are defining a new function. We are naming it hello. The following lines are indented to show that they are part of the hello function. Here's a note. Some shells will print ellipses. Open bracket, open quote, dot, 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 close quote, end parentheses. No, it's not a parentheses, it's square. Bracket, that's the word. At the beginning of the indented lines. The blank line at the end obtained by hitting the Enter key twice lets Python know that the definition is finished and the shell responds with another prompt. Notice that typing the definition did not cause Python to print anything yet. We have told Python what should happen when the hello function is used as a command. We haven't actually asked Python to perform it yet. A function is invoked or called by typing its name followed by parentheses. Here's what happens when we use our hello command. Arrow, 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 hello, open parentheses, close parentheses. Hello. Computers are fun, exclamation point, arrow, arrow, arrow. Do you see what this does? The two print statements from the hello function definition are executed in sequence. You may be wondering about the parentheses in the definition and use of hello. Commands have changeable parts called parameters, also called arguments, that are placed within the parentheses. Let's look at an example of a customized greeting using a parameter. First, the definition. Arrow, 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 def, greet, open parentheses, person, close parentheses, colon. Next line, print, open parentheses, quote, hello, end quote, comma, person, close parentheses. Next line, print, open parentheses, quote, how are you, question mark, end quote, end parentheses. Now we can use our customized greeting. Greet, John. Hello, John. How are you? Arrow, arrow, arrow. Greet, Emily. Hello, Emily. How are you, question mark. Arrow, arrow, arrow. Can you see what is happening here? When using greet, we can send different names to customize the result. You might also notice that this looks similar to the print statements from before. In Python, print is an example of a built-in function. When we call the print function, the parameters in the parentheses tell the function what to print. We will discuss parameters in detail later on. For the time being, the important thing to remember is that the parentheses must be included after the function name whenever we want to execute a function. This is true when no parameters are given. For example, you can create a blank line of input using print without any parameters. Arrow, 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 print, open parentheses, close parentheses, arrow, arrow, arrow. But if you type just the name of the function, omitting the parentheses, the function will not actually execute. Instead, an interactive Python will show some output indicating what function that name refers to, as this interaction shows. Arrow, 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 greet. Backwards arrow? I don't know. Left arrow? Function greet at 0 times 8393 AEC arrow. Arrow, 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 print. left arrow, built-in function print, right facing arrow. The funny text 0 time or 0x8393AEC is the location or the address in computer memory where the greet function definition happens to be stored. If you are trying this out on your own computer, you will almost certainly see a different address. One problem with entering functions interactively into a Python shell, as we did with the hello and greet examples, is the definitions are lost when we quit the shell. If we want to use them again the next time, we have to type them all over again. Programs are usually created by typing definitions into a separate file called a module or a script. This file is saved in secondary memory so that it can be used over and over again. A module file is just a file of text, and you can create one using any application for editing text, such as Notepad or a word processor, provided you save your program as a plain text file. A special type of application known as an integrated development environment simplifies the process, also called an IDE. An IDE is specifically designed to help programmers write programs and includes features such as automatic indenting, color highlighting, and interactive development. Idle is a good example. So far, we have just been using idle as a Python shell, but it is actually a simple but complete development environment. Footnote number 2. In fact, IDLE stands for Integrated Development Environment. The extra L is thrown in tribute of Eric Idle of Monty Python fame. All right, back to the paragraph. Let's illustrate the use of a module file by writing and running a complete program. Our program will explore a mathematical concept known as chaos. To type this program into idle, you should select the File/New File menu option. This brings up a blank non-shell window where you can type a program. Here is the Python code for our program. Hashtag or # file : chaos.py. Hashtag a simple program illustrating chaotic behavior, period. Def main, open parentheses, close parentheses, : print, open parentheses, open quote. This program illustrates a chaotic function, end quote, end parentheses. X equals eval, open parentheses, input, open parentheses, open quote, enter a number between 0 and 1, : end quote, end parentheses, end parentheses. For I in range, open parentheses, 10, close parentheses, : X equals 3.9 star X star, open parentheses, 1 minus X, close parentheses, print, parentheses, X, close parentheses, main, open parentheses, close parentheses. Once you have typed it in, select File/Save from the menu and save it with the name chaos.py. The .py extension indicates that this is a Python module. Be careful where you save your program. Sometimes idle starts you out in the system-wide Python folder by default. Make sure to navigate to a folder where you keep your own files. I'd suggest keeping all your Python programs together in a dedicated folder in your own personal document area. At this point, you may be trying to make sense out of what you just typed. You can see that this particular example contains lines to define a new function called main, right? Open parentheses. Programs are often placed in a function called main, close parentheses. The last line of the file is the command to invoke this function. Don't worry if you don't understand what main actually does. We will discuss it in the next section. The point here is that once we have a program saved in a module file like this, we can run it anytime we want. Our program can be run in a number of different ways that depend on the actual operating system and programming environment that you are using. If you are using a windowing system, you can probably run a Python program by clicking or double-clicking on the module's files on the module files icon. In a command line situation, you might type a command like python chaos.py. When using idle, you can run a program simply by selecting run/run module from the module window menu. Hitting the F5 key is a handy shortcut for this operation. When idle runs the program, control will shift over to the shell window. Here is how that looks. Arrow, 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 lots of dashes, restart, lots of dashes, or lots of equal signs actually. Arrow, arrow, arrow. This program illustrates a chaotic function. Enter a number between 0 and 1 colon 0.25. 0.73125, 0.76644140625. Do I need to read all of these numbers? I don't think so. Skipping to the end, arrow, arrow, arrow. The first line is a notification from idle indicating that the shell has restarted. Idle does this each time you run a program so that the program runs in a pristine environment. Python then runs the module from top to bottom, line by line. It's just as if we had typed them one by one at the interactive Python prompt. The def in the module causes Python to create the main function. The last line of this module causes Python to invoke the main function. Did I just read that twice? Thus running our program. The running program asks the user to enter a number between 0 and 1. In this case, I typed 0.25. And then prints out a series of 10 numbers. If you browse through the files on your computer, you may notice that Python sometimes creates another folder called __py cache __ inside the folder where your module files are stored. This is a place where Python stashes companion files with a PYC extension. In this example, Python might create another file called chaos.pyc. This is an intermediate file used by the Python interpreter. Technically, Python uses a hybrid compiling interpreting process. The Python source in the module file is compiled into more primitive instructions called bytecode. This bytecode, the .pyc, is then interpreted. Having a .pyc file available makes running a module faster the second time around. However, you may delete the bytecode files if you wish to save disk space. Python will automatically recreate them as needed. Running a module under idle leads the program into the shell window. You can run the program again by asking Python to execute the main command. Simply type the command at the shell prompt. Continuing with our example, here's how it looks when we rerun the program with 0.26 as the input. And it's going to look similar, but it's going to call up a different set of random numbers between 0 and 1. Several of them start with 0.7. I'm going to shift my seat because it's getting uncomfortable here. I'll put down a pillow. Excuse my interruption. You can always just speed up the video if you like. Section 1.7, inside a Python program. The output from the chaos program may not look very exciting, but it illustrates a very interesting phenomenon known to physicists and mathematicians. Let's take a look at this program line by line and see what it does. Don't worry about understanding every detail right away. We will be returning to all of these ideas in the next chapter. Excuse me while I pause for a second. Wow, chapter 1 is long. The first two lines of the program start with the hashtag or pound character, pound hashtag file, chaos.py, hashtag, a simple program illustrating chaotic behavior. These lines are called comments. They are intended for human readers of the program and are ignored by Python. The Python interpreter always skips any text from the pound sign through the end of a line. The next line of the program begins with the definition of a function called main, def main, open parentheses, close parentheses, colon. Strictly speaking, it would not be necessary to create a main function, since the lines of a module are executed as they are loaded. We could have written our program without this definition. That is, the module could have looked like this: pound sign, file, colon, chaos.py, that's not a colon, pound sign, a simple program illustrating chaotic behavior, print, open parentheses, open quote. This program illustrates a chaotic function, end quote, end parentheses. X equals eval, open parentheses, input, open parentheses, open quote. Enter a number between 0 and 1, colon, end quote, end parentheses, end parentheses. For I in range, open parentheses, 10, close parentheses, colon. X equals 3.9 star X star, open parentheses, 1 minus X, close parentheses. Next line, print, open parentheses, X, close parentheses. This version is a bit shorter, but it is customary to place the instructions that comprise a program inside of a function called main. One immediate benefit of this approach was illustrated above. It allows us to run the program by simply invoking main, open parentheses, close parentheses. We don't have to restart the Python shell in order to run it again, which would be necessary in the main-less case. The first line, the mainless, like not using the main function, now I get it, main-less case. The first line inside of main is really the beginning of our program. Print, open parentheses, open quote. This program illustrates a chaotic function, end quote, end parentheses. This line causes Python to print a message introducing the program when it runs. Take a look at the next line of program. X equals eval, open parentheses, input, open parentheses, open quote. Enter a number between 0 and 1, colon, end quote, end parentheses, end parentheses. Here, X is an example of a variable. A variable is used to give a name to a value so that we can refer to it at other points in the program. The entire line statement to get some input the entire line is a statement to get some input from the user. There's quite a bit going on in this line, and we'll discuss the details in the next chapter. For now, you just need to know what it accomplishes. When Python gets to this statement, it displays the quoted message, enter a number between 0 and 1, colon, and then pauses, waiting for the user to type something on the keyboard and press the enter key. The value that the user types is then stored as the variable X. In the first example shown above, the user entered 0.25, which becomes the new value of X. The next statement is an example of a loop. For I in range, open parentheses, 10, close parentheses, that's a colon. A loop is a device that tells Python to do the same thing over and over again. This particular loop says to do something 10 times. The line indented underneath the loop heading, under the loop heading, are the statements that are done 10 times. These form the body of the loop. X equals 3.9 star X star, open parentheses, 1 minus X, close parentheses, print, open parentheses, X, close parentheses. The effect of the loop is exactly the same as if we had written the body of the loop 10 times. X equals 3.9 star X star, open parentheses, 1 minus X, close parentheses, print, open parentheses, X, close parentheses. And it repeats that 10 times. I do hope you're following along in a book. Print X. X equals 3.9 star X star, open parentheses, 1 minus X, close parentheses, print x inside of parentheses. Obviously, using the loop instead saves the programmer a lot of trouble. But what exactly do these statements do? The first one performs a calculation, x equals 3.9 star x star, open parentheses, 1 minus x, close parentheses. This is called an assignment statement. The part on the right side of the equal is a mathematical expression. Python uses the star character to indicate multiplication. Recall that the value of x is 0.25 from the input above. The computed value is 3.9, open parentheses, 0.25, close parentheses, open parentheses, 1 minus 0.25, close parentheses, or 0.73125. Once the value on the right-hand side is computed, it is saved as or assigned to the variable that appears on the left-hand side of the equals. In this case, x. The new value of x is now 0.73125. It replaces the old value of 0.25. The second line in the loop body is a type of statement we have encountered before, a print statement. Print x. When Python executes this statement, the current value of x is displayed on the screen. So the first number of output is 0.73125. Remember that the loop executes 10 times. After printing the value of x, the two statements of the loop are executed again. X equals 3.9 star x star, open parentheses, 1 minus x, close parentheses, print x inside parentheses. Of course, now x has the value of 0.73125. So the formula computes a new value as 3.9, open parentheses, 0.73125, close parentheses, open parentheses, 1 minus 0.73125, end parentheses, which is now 0.76644140625. Can you see how the current value of x is used to compute a new value each time around the loop? Yes, I see it. That's where the numbers in the example run come from. You might try working through the steps of the program yourself for a different input value, let's say 0.5. Then run the program using Python to see how well you did impersonating a computer. I'll impersonate a computer if you want me to, but I don't know. 1.8 chaos and computers. Okay. I said above that the chaos program illustrates an interesting phenomenon. What could be interesting about a screen full of numbers? If you try out the program for yourself, then you will find that no matter what number you start with, the results are always similar. The program spits back 10 seemingly random numbers between 0 and 1. As the program runs, the value of x seems to jump around, well, chaotically. The function computed by this program has the general form k parentheses x and parentheses, open parentheses, 1 minus x and parentheses, where k is in this case is 3.9. This is called a logistic function. It models certain kinds of unstable electronic circuits and is also sometimes used to model population variation under limiting conditions. Repeated application of the logistic function can produce chaos. Although our program is a well-defined underlying behavior, the output seems unpredictable. An interesting property of chaotic functions is that very small differences in the initial value can lead to large differences in the result as the formula is repeatedly applied. You can see this in the chaos program by entering numbers that differ by only a very small amount. Here is the output from a modified program that shows the results of initial values of 0.25 and 0.26 side by side. So if we look at them side by side, they look pretty well near one another. Would you like a look at the list of numbers? I don't know that my camera is the best, but they are very similar. So with very similar starting values, the output stays similar for a few iterations, but then they start to differ markedly. But about the fifth iteration, there no longer seems to be any relationship between the two models. These two features of our chaos program, apparently unpredictability and extreme sensitivity to initial values, are the hallmarks of chaotic behavior. Chaos has important implications for computer science. It turns out that many phenomena in the real world that we might like to model and predict with our computers exhibit just this kind of chaotic behavior. You may have heard of the so-called butterfly effect. Computer models that are used to simulate and predict weather patterns are so sensitive that the effect of a single butterfly flapping its wings in New Jersey might make the difference of whether or not rain is going to be predicted in Peoria. It's very possible that even with perfect computer modeling, we might never be able to measure existing weather conditions accurately enough, to predict weather more than a few days in advance. The measurements simply can't be precise enough to make the predictions accurate over a longer time frame. As you can see, this small program has a valuable lesson to teach users of computers. As amazing as computers are, the results that they give us are only as useful as the mathematical models on which the programs are based. Computers can give incorrect results because of errors in programs, but even correct programs may produce erroneous results if the models are wrong or the initial inputs are not accurate enough. Section 1.9. This chapter is the chapter summary. This chapter has introduced computers, computer science, and programming. Here is a summary of some of the key concepts. 1. A computer is a universal information processing machine. It can carry out any process that can be described in sufficient detail. A description of the sequence of steps for solving a particular problem is called an algorithm. Algorithms can be turned into software programs that determines what the hardware, the physical machine, can and does accomplish. The process of creating software is called programming. Number 2. Computer science is the study of what can be computed. Computer scientists use techniques of design, analysis, and experimentation. Computer science is the foundation of the broader field of computing, which includes areas such as networking, databases, and information management systems, to name a few. Third, a basic functional view of computer systems comprises a central processing unit, or CPU, the main memory, secondary memory, and input and output devices. The CPU is the brain of the computer that performs simple arithmetic and logic operations. Information that the CPU acts on, the data, the programs, is stored in main memory, RAM. More permanent information is stored on secondary memory devices such as magnetic disks, flash memory, or optical devices. Information is entered into the computer via input devices, and output devices display the results. Next, programs are written using a formal notation known as a programming language. There are many different languages, but all share the property of having a precise syntax or form, and semantics, meaning. Computer hardware understands only a very low-level language known as machine language. Programs are usually written using human-oriented high-level languages such as Python. A high-level language must either be compiled or interpreted in order for the computer to understand it. High-level languages are more portable than machine language. Next, Python is an interpreted language. One good way to learn about Python is to use an interactive shell for experimentation. The standard Python distribution includes a program called idle that provides a shell as well as facilities for editing Python programs. Next section, a Python program is a sequence of commands called statements for the Python interpreter to execute. Python includes statements to do things such as print output to the screen, get input from the user, calculate the value of the mathematical expression, and perform a sequence of statements multiple times, called a loop. And finally, a mathematical model is called chaotic if very small changes in the input lead to large changes in the results, making them seem random or unpredictable. The models of many real-world phenomena exhibit chaotic behavior, which places some limits on the power of computing. Exercise 1.10 is some review questions in the form of true and false. Computer science is the study of computers. True or false? No, they said the computers are the tool you use, like a telescope, to study astronomy. You use a computer to study computers, I guess. The CPU is the brain of the computer. I do believe that's what they have said twice now. So I'm going to go with true on that one. Let me know in the comments if you disagree. Secondary memory is also called RAM. I thought the secondary memory was when you put it onto a disk or a more permanent information. Let's see, back in this paragraph. Information that the CPU acts on is stored in the main memory. So which one is considered secondary? Secondary memory? Oh, the CPU is the main memory. And then I guess RAM is the secondary memory. And then the more permanent memory is the magnetic disks, flash memory, and optical devices. So I'm going to go with that. So yes, the RAM is the secondary memory. All information that a computer is currently working on is stored in main memory. No, because it can be pulling from the other areas also. So I would say that one is false. Let me know if you disagree with number 4. All information that a computer is currently working on is stored in the main memory. I don't believe that's true. I believe that is false. Number 5, the syntax of a language is its meaning. The semantics is its form. They reversed that, so that is false. Precise syntax is form, and semantics is meaning. They tried to trick us there. Let's see, number 6, a function definition is a sequence of statements that defines a new command. I'm going to get stuck, and you guys are going to call me out. A function definition is a sequence of statements that defines a new command. It sounds reasonable. I'm going to go true. That if I have a function definition as a sequence of statements, that could be a new computer command. I think so. Number 7, a programming environment refers to a place where programmers work. No, you can't trick me with that one. It's not. It's on the computer. It's not in the environment around the worker, the programmer. Number 8, a variable is used to give a name to a value so that it can be referred to in other places. I agree with that. That's true. Number 9, a loop is used to skip over a section of program. That's not true. It's used to repeatedly run a program. So number 9, you are false. Number 10, a chaotic function can't be computed by a computer. Well, that's false because they just gave us several examples where they computed it out to get the seemingly random responses. Okay, there are multiple choice questions, there are discussion questions, there are programming exercises, and I am not going to continue to do that together with you here live. So if you do those and you want to discuss those, feel free to put them in the chat. I do hope that this video is beneficial to you if you are taking this course or if you are using this textbook to help you get through all of this material. If you are an auditory learner or if you are wanting the auditory in addition to the visual, and I am so glad that you joined me to hear this. and I will see you in the next one. Goodbye. Yes, end.